Hi there. I decided to do a video answer for this question because it's quite a bit more graphic, uh, laden, and it's laden with graphic solution. So you need to show this graphically in order for you to understand it. Okay. So what do you have here? You have a bucket that is being lifted off the ground here, a distance of 15 meter, and you're asked to find. That's a bucket here. And that bucket is full of sand. The bucket weighs, when it's up there, it weighs 20 kilogram. Its mass is 20 kilogram because when it was on the ground here, this is a bucket on the ground, it used to weigh 25 pounds, 25 kilograms, 25 kilograms. So when the bucket was lifted, it basically, there's work being exerted or work being done on this bucket in order for it to lift it up. So the work that you have here is you have two types of works. You have what's called fixed work, and you have, on this case here, this is a rope that's suspended to it, and got a tie here, and you got a condition where you have a variable work. So what is it work on this bucket here in the fixed condition? We'll start with the fixed condition because that's the easiest. Okay. First of all, you have to understand that when the bucket is lifted up to the 15-meter range, the weight of the rope is no longer affected. Does not affect the weight here because the rope is being pulled. It's either rolled or it's basically, when the bucket is here, the weight of the rope is not included. So you're given here that the weight of the rope is 0.3 kilogram per meter. And you're also given that there is 1 meter you need here in order to tie this bucket to the rope. So there's 1 meter of bucket, 1 meter of rope. Okay. So what would be the weight of the bucket in the fixed work condition when it's in this position right here? When it's in this position right here? Well, the work is going to be, let me change the color of this pen a little bit, change it to blue. The work is going to be the force times distance cosine theta. But since theta here is 0, then cosine 0 is 1. Theta is 0 because it's 0 from the y-axis. So the work is equal to the force times distance. So the force is basically the mass times the gravitational acceleration, which is that. So this is the mass here, mass equal 20 kilogram, but the force itself, F, is equal to mg. Okay, so mg times the distance here from the ground to where the bucket is, and that's 15 meter. We call that h. So actually the work is also called the potential energy. Potential energy is equal to the mass times the gravitational acceleration times the height. Okay, so what is the mass of this thing? Well, you've got 20 kilogram plus you've got the rope that's tied here to the top of the bucket. That's another 0.3 kilogram per meter, and you have 1 meter of rope based on problem statement. So that's 0.3 kilogram. So your total mass is 20 plus 0.3 kilogram. That is your mass. We're talking here for the fixed condition, okay? The fixed work. So times the gravitational acceleration, which is 9.8 meter per second squared. Some people use 9.81. It doesn't matter. I'm just going to use 9.8 meter per second squared times the height, which is 15 meter. So if you calculate this, you're going to get 20.3 times 9.8 times 15. So your total work is 2984. What? Kilogram meter per second squared times meter gives you kilogram meter squared per second squared. Meter squared per second squared. And that is a unit of joules. So 2984 joules. Okay. So this is your work, the fixed part, fixed work. So what about when you lifted this bucket up to this position? What was the weight then? Okay, so here you are into the variable type of work, which you're going to have to do some calculus and solve some integration in order for you to find this work. Okay, so basically what we're saying is the total weight, including the rope here, is going to be 25 kilogram plus the length of the rope is 15 meter plus the 1 meter that's tied to the bucket. So that's 16 meter plus 16 meter times 0.3 kilogram per meter. Right? So that is, so meter and meter cancels out. You get in the mass, let's call this mass big M, just to not to confuse with the other one. So let's call this mass big M is really equal to 25 plus 16 times 0.3. 25 plus 16 times 0.3. 29.8 what kilogram. Now, in order for you to solve this, like I said, you have to incrementally basically use a series of evaluations until you get to the top, which changes as you go up because the bucket is basically losing weight because it starts with 25, it has a hole in it. As you lift it up all the way to here, it becomes 20 kilogram. So between 25 and 20 kilogram, there's a loss of 5 kilogram of sand. Okay, so that has to be accounted here somewhere, and we're going to kind of work with it. So when it was on the ground, if we are to solve this mass per unit length, call that M per L, will be 29.8 kilogram divided by 15. and that comes to 1.98 kilogram per meter. 1.98 kilogram per meter. Okay. So the variable weight as it's being lifted when it started here, it's 1.98 kilogram per meter, but that basically changes because the force is changing. As we go up, the force, we call that the change in the force is going to be what? The 1.98 kilogram per meter, kilogram per meter, delta F, so times delta Y. Okay. Why? Because the change in the force is equal to the weight per unit meter times the change in elevation, which is delta Y. Okay, this is very important for you to understand, so we could kind of solve this problem. So if this is the change in the force, what would be the change in the work? Well, the change in the work is going to be 1.98 kilogram per meter times, we go from 15 meter to nothing here. So will be times 15 minus y delta y. Okay. So we need to integrate this value here on what? We need to integrate from 0 to 15 meters. So the bounds of this integration is going to be 0 to 15 meters. So I'm going to start on a different second board. I'm going to write that delta y, again, I'll write what delta w, which is change in work is equal to 1.98 times 15 minus y delta y. Okay. So if I am to integrate this, what would be the bounds? So the work is going to be the integral of 1.98 times 15 minus y dy. And what would be the bounds? From 0 to 15 meters. Those are your bounds. Okay. When you integrate this, you will get a value in terms of y, which is basically the height of the bucket as it goes up. So this will become 1.98 outside, integral from 0 to 15 of 15 minus y dy. We'll use that 1.8 as a constant and we'll put it outside the integration. So that will be 1.98. Now I'll solve the integral. The integral is 15y minus y squared over 2. And since this is a definite integral, so it goes from 0 to 15. You have to evaluate it from 0 to 15. So you're going to get 1.98. Let me write up here. So I'm going to conserve the place, conserve enough space. So we're 1.98. And what's the unit of 1.98? Kilogram per meter. And this will going to give you 15. If you evaluate this, you get 15 times 15 minus 15 squared over 2. And this is going to be 1.98 kilogram per meter times 15 times 15 is 225. Okay. And 15 squared over 2 is 225 over 2 is 112.5. So if you solve this, you get 1.98 kilogram per meter times 225 minus 112.5 is 112.5. What? Meter squared. Okay, just want to make sure the unit. So meter squared cancel out. You get meter here. You're going to get an answer in kilogram meter. Okay, so you get, just multiply 1.98 times 112.5, 222.7, I'm going to call it 223 kilogram meter. But this is not the unit of work. Well, we forgot to multiply by G, right? So we multiply by G becomes, what is a unit of G? Well, it'll be 223 kilogram times meter times 9.81, 9.8 Newton per what? 9.81, sorry, meter per second squared, not Newton, meter per second squared. So that's going to give me 223 times 9.8, 2185 kilogram times meter squared per second squared. Kilogram times meter squared per second squared. Well, this is a unit of joules. So this will be 2185 joules. Okay. Now, what would be the total work? The total work will be the work fixed, sum of the work fixed, plus sum of the work variable. Sum of the fixed work plus sum of the variable work. Variable. What was the fixed work? Was 2984 joules. Joules plus work variable was 2185 joules. Add both of those up, you get 2984 plus 2185, you get 5169 5169 joules, and this is your problem. Okay, if you like what you see, contact me on Wyzant for another lesson or for other problems that you might have. Take care.